Okay, now we're on page 46 in the second page of the review. So on this page, problem 6 starts out with what mass of Ag, or silver, can be produced when 5 grams of copper reacts with 20 grams of silver nitrate. So this looks like, again, a limiting reactant problem because we're given 2 amounts of reactants. So that means we need to, again, and I'm going to do this on a separate sheet again, go from both amounts of reactant, 5.00 grams of copper to grams of silver, and then 20.0 grams of silver nitrate to grams of silver. Now, similar to the last page, let's just go from grams to grams 2 more times. Copper is on the periodic table 63.55 grams per mole. We now need the balanced equation ratios. And again, this problem was already balanced because the numbers were already there. So for every 1 mole of copper, we produce 2 moles of Ag. And then the molar mass of Ag for every 1 mole of Ag, silver is 107.87 grams per mole. So let's multiply everything on top and divide by everything on bottom. And we get 16.97, so that actually rounds up to 17.0 grams of Ag. Now let's do the same thing with silver nitrate. So now this time we need to add 107.87, the molar mass of silver, plus 14.01, the molar mass of nitrogen, plus 3 oxygens, which would be 3 times 16. And we get 169.88 grams of silver nitrate per 1 mole of silver nitrate. Now, the balanced equation ratios for silver nitrate and silver are a 2-to-2 ratio. So let's put 2 moles of silver nitrate on bottom and 2 moles of Ag on top. And then again, the last thing we need to do is multiply by that molar mass of silver, which is 107.87 grams of silver per 1 mole of silver. Let's multiply everything on top and divide by everything on bottom. And this time we get 12.7 grams of silver. So it looks like this is how much silver can actually be made. Now problem B again asked for what mass of excess will be left over. We're getting a lot of practice with this right now. Start with the product made. And let's go back and let's state that AgNO3 is the limiting reactant because it ran out, and copper must then be the excess reactant. So let's go from 12.7 grams of Ag to grams of excess that was used. The molar mass of silver is 107.87 grams per 1 mole. The mole ratios from the balanced equation again are for every 2 moles of Ag, we needed 1 mole of copper. And then the molar mass of copper for every 1 mole of copper, we have 63.55 grams of copper. Multiply everything on top. Divide by everything on bottom. And we get 3.74 grams of copper were used. Now again, we're not done. This is just say how much copper we needed. We started with 5 grams of copper. That was given to us, and we used 3.74 grams of copper. So it looks like 1.36 grams of copper would be left over. Okay. For problem 7, give the following reaction. Fill in the box to show what molecules will be present when the reaction reaches completion. This is something we practiced on Wednesday. So let's start by looking at the ratios from the balanced equation. For every 2 moles of water, it reacts with 1 mole of oxygen to produce 2 moles of H2O2 or hydrogen peroxide. So I like the circling method. So for every 2 H2O and 1 O2, we're going to make 2 H2O. So So there's one H2O, H2O2. There's two H2O2. These two were made from these three molecules right here. Now another two waters and one oxygen are going to produce another two H2O2s. Now what happens with these two oxygens? I guess those guys are left over. So if the oxygens are left over, they would be excess reactants. And that makes the waters the limiting. Now down below, it says, write the reaction that's represented by the next two pictures. So this first picture, let's first look at, if anything is left over, let's get rid of it. So I see these two X's on both sides, so let's get rid of 1, 2, 3, 4 of them. Those didn't react. They're not a part of this reaction. It looks like we now have 3x2 plus 3y2 forming 1, 2, 3, 4, 5, 6xy. Now we can't end with this because it's not simplifying. We always simplify. So we can divide everything by 3 and get x2 plus y2 makes 2xy. And that is the balanced equation to represent these pictures. Let's try that one more time. Again, let's find whatever is left over still and get rid of it from both sides. It looks like one of these y's is there. It looks like we have another one still left over. We have another one, and we have another one. Again, I'm crossing these out from both sides because they never technically reacted. Now let's look at what we have left. I have 1, 2, 3, 4 x3. And I have 1, 2, 3, 4, 5, 6y. I have that producing 1, 2, 3, 4, 5, 6 H2Os. I'm sorry, x2, 6, x2y. Now again, we can simplify these, so let's get rid of, let's divide everything by 2, and we get 2x3 plus 3y yields 3x2y. And there's the simplified reaction to represent this. Okay, question 9. It says calculate the percent of water, which is H2O, in nickel 2. Now we need to know the formula for this. Nickel 2 is Ni plus 2. Chloride, it's a Cl minus 1. So that means it's NiCl2. And hexahydrate, don't be expected to remember this for the test. We would tell you this, but this just means you have 6 H2Os bonded to all of this. And the question wants to know what percent of this molecule is water. So what we need to do is get the total molar mass and then divide the mass of the water by that. So 6 waters, 6 H2Os would equal 6 times 18.02. And that is 108.12. And then we need to add to this the entire substance. So the nickel chloride, we would add to that 1 nickel, which is 58.69, and then 2 chlorines, which are 35.45 times 2. So that means the total molecule is 237.71 grams per mole. So to solve this, we do the water, 108.12 grams per mole, divided by the total, 237.71 grams per mole. And we get 0.4548. So I would multiply that by 100 because the decimal or the fraction just represents the, not the percentage yet. This would be 45.5%. And that's all you really have to know about how to do percent composition. Now for kinetics. What 2 requirements are needed in order for a collision to lead to a chemical reaction? They have to collide, and that just means hit, in the correct spot. We usually use the word orientation or maybe angle. And they also have to collide hard enough or with enough force, with enough energy. So explain why reaction rates vary with temperature. Well, temperature is really the measure of how fast particles are moving. So temperature equals speed, technically. So you can actually think of this, when you go outside on a cold day, it means the air particles are moving slowly. When you go out on a really hot day, the air particles are moving really quickly. So if we increase the temperature, that means we're going to have more collisions. So if we increase temp, you're going to have more collisions. And since they're also flying around faster, they're also going to be harder collisions. So if you wanted to speed up a reaction, you could maybe increase the temperature of the reaction. If you want to slow down a reaction, decrease the temperature of the reaction. Other than temperature, name 3 other factors that will affect reaction rates. Well, we talked about surface area. Again, if you increase the surface area, you're just allowing for more collisions. Concentration is talking about how much stuff you have, essentially. So if you give more stuff in one area or one volume, there's a greater chance of collision. So everything kind of gets into relating to that word collision. And then lastly, we don't expect you to know too much about this, but adding a catalyst also will speed up a reaction. Explain why a pound of iron filings, that's like iron dust, would rust faster than a 1 pound block of solid iron. Iron filings would have a greater surface area. And that would just mean there's a greater chance of having more collisions with the oxygen in the air. Last question. Give 2 changes that could make to slow a reaction down and explain why each one would work. If you want to slow a reaction down, I would decrease the temperature, because that means molecules are moving slowly or particles are moving slowly. And if particles are moving slower, there's going to be fewer collisions. And also collisions with less force. Also, we could, decrease surface area, decrease concentration. In both of those situations, again, all you're doing is you're decreasing, or you're making fewer collisions between the reactants.